Well, thank you for waiting so long to come in. It's a real pleasure to be here in Athens and have the opportunity to tell you a bit about our work. So I'm a neuroscientist. I focus on the brain. And the brain's a very complicated organ, very difficult to understand, as you know. But I want to start with the simplest question you can ever ask about the brain, and one which we as neuroscientists really should ask ourselves very early in our careers, and one which I think every school student really should ask themselves. And that is, why do we and other animals have brains? It's a pretty fundamental question because there are many species on our planet who don't have brains. So why did we evolve this brain-like organism? Now, if you think about this question for any length of time, it becomes obvious. There's one reason and one reason only to have a brain, and that's to produce adaptable and complex movements. Now, that may seem surprising to you, but if you think about it, movement is the only way you have to affect the world around you. Now, that's not quite true. There's one other way going on right now, and that's through sweating. But if you take sweating out of the picture, everything else goes through the contraction of muscles. So think about communication, speech, gestures, writing, sign language. They all require movement to express yourself on the outside world. So it's important, if you're going to think about the brain, to realize that sensory, memory, and cognitive processes are all important, but they're actually only important to either drive or suppress future movements. There can be no evolutionary advantage to having memories of childhood or perceiving the color of a rose if it's not going to affect the way you're going to move later in life. Now, for those who don't believe in this argument, here's the clinching evidence. This is the sea squirt. It's a very rudimentary animal, and it swims in the ocean in its juvenile life, and it has a nervous system and an eye, and at some point it implants on a rock, and having implanted on that rock, it never leaves that rock again. And the first thing it does when implanting on that rock is to digest its own brain and nervous system for food. So once you don't need to move, you no longer need the luxury of that brain. And in fact, the sea squirt is taken as an analogy to what happens in my own university, Cambridge, when people are promoted to professors. So I am a movement chauvinist. I believe movement is the most important thing the brain does. Now, clearly, these things are all important. We have to understand them, but we have to remember what they're there for. They're there to make you move. Now, if movement is so important, we can ask, how well are we doing understanding how the brain controls movement? And the answer is a very difficult problem. And I can illustrate how difficult it is by thinking about how well we do to build machines which can do what humans can do. If we take the game of chess here, and we pitch Garry Kasparov when he's not in jail against IBM's Deep Blue, the answer is IBM's Deep Blue will occasionally win. And I expect, although I can't be sure, if the computer played anyone in this room, it would probably win every time. That problem is effectively solved. What about the problem of picking up a chess piece, dexterously manipulating it and putting it back down on the board? Pit a 6-year-old child's dexterity against the best robots today, there's no competition. The 6-year-old outplays a robot in terms of manual dexterity. So why is this problem so easy and this one so hard? And one reason is a smart 6-year-old could tell you the algorithm or computer code required to solve this top one. The algorithm's really simple. Look at all possible moves to the end of the game and choose the one that makes you win. Now, clearly we know there's a combinatorial explosion of possibilities, so you need fast computers and some approximations. But we basically know how to go about solving that. When it comes to being dexterous, we simply don't know the algorithm or computer code we need to be dexterous. And as I'll illustrate, there are extra difficulties in both sensing the world and acting on the world, which lead to a huge amount of uncertainty. Now, what I want to illustrate, maybe for those who aren't familiar with cutting edge in these two, is sort of the cutting edge of robotics. This is the end of a 3-year... Can we keep the lights up? It's nicer with the lights up, unless people don't like it. This is the end of a 3-year PhD. Not the best student, not the worst. It's able to get this bottle poured into the glass. It's hard because the bottle's squeezy and the water spills around. But effectively, they can do this, and it doesn't do it with any near the dexterity that we as humans do it. Now, if you want this robot to do a different task, that's another 3-year PhD. There's no generalization in robotics from one task to another. Each are hand-tailored to solve a particular problem. And that's a frustration for roboticists and for us. Now, we can compare that to Emily Fox here. Here's Emily Fox, who's going to have a go at winning the world record for cup stacking. Now, I expect, like Britain, cup stacking is probably not a very popular sport in Greece. But in America, it's a very popular high school sport. You have 12 cups. You have to stack and unstack in the prescribed order against the clock. And this in real time is her world record attempt. And she got the world record. We have no idea what is going on inside her brain when she does that. And that's what we try to work out. We try to reverse engineer how people have such amazing dexterity. So I want to focus on two features, or one feature really, which makes that control problem hard. And that's the fact of noise. Now, I'm going to talk about noise not in the everyday sense of sound. When I talk about noise, I'm talking in the engineering or neuroscience sense of a random disturbance to a signal. It comes from the old days when you had to tune your old-fashioned radios and you had on the station you want to hear. That was the noise riding on the signal or music you wanted to hear. And the trouble is, when you send a command down to move your muscles, and it contracts and the arm moves, and you get sensory feedback from vision, from the skin, the muscles, and the joints, these signals are not the beautiful signals you want. For example, sensory feedback is extremely noisy. If you put your hand under a table and try to localize with the other hand, you can be off by many centimeters. Similarly, the movement commands themselves are very noisy. If you try to make the same movement over and over again, such as trying to hit a position on the dartboard, you have a huge amount of scatter. And the tasks we perform are both ambiguous and variable. This teapot can be full, it can be empty, it can change with time. So we work in a sensory movement and task soup of noise. Now, this noise is so great that our society will reward people if they can reduce the sensory, motor, and task noise. So if you're lucky enough to be able to hit a small white ball into a hole several hundred yards away with a long metal stick, then people will reward you with hundreds of millions of dollars. But I want to convince you that it's not only in sports that we care about this noise. The brain goes to a lot of effort to reduce this sort of uncertainty. So noise is one sort of uncertainty, which makes life hard for control. But there's another sort of uncertainty, which is ambiguity. So there are many things, however long you try to sense them, you can't distinguish between. So you're a three-dimensional world out there, and I can see you all, but the back of my eyes are two-dimensional. So I take this three-dimensional world, and I put a projection into two dimensions, so I lose information. And once I lose that information, that's a problem for interpretation of the scene. So take this example here. Imagine that was the image at the back of your eye. It could have come from this object, or this object, or this object, all produce the same two-dimensional image on the back of the eye. And in fact, there are an infinite number of objects which will give you the same vision at the back of your eye. And therefore, distinction between them is a big problem. Similarly, if I take this object and I put it behind an occluder, so now you can just see a bit of it, and I set the object in motion, and I say, how is that square moving? Most of you will say it's moving left and right. But that wasn't the case. If I show you what was really happening, the object was going round in a circle. Yet you perceive it as left and right because it's ambiguous. And the question is, why did you choose that interpretation out of all possible interpretations? And we'll come back to both these examples. So the framework which has become dominant for understanding how the brain deals with uncertainty is Bayesian decision theory. So this is Thomas Bayes. He lived in the 1700s. He was an English cleric or vicar. He wasn't particularly famous in his lifetime. But after he died, a friend of his found an interesting mathematical paper among his possessions and thought it so interesting, he sent it into the editor of the Philosophical Transactions of the Royal Society, a very popular journal at the time, saying, I now send you an essay which I have found among the papers of our deceased friend, Mr. Bayes, and which, in my opinion, has great merit. Now, fortunately for us, the editor of that journal is not as difficult as he is today and did not ask for major revisions to the article, given the author was dead, and instead published it as it is, Essays Towards Solving a Problem in the Doctrine of Chances. It was forgotten really for hundreds of years, but from the 1950s onwards, it's become a major part of statistics and machine learning, and more recently a unifying way to think about how the brain might deal with uncertainty. So it's become a very powerful technique. And the basic idea now is there are two parts to it. There's what's called Bayesian statistics, and that's about making inferences based on uncertain observations of the world. So how do I decide whether you're a cat or a dog, whether you're a friend or a foe, where my arms are? Those are the inferences I might want to make. And the second part is the decision theory. Having made my inferences about the world, how do I decide what to do? Now, I'm going to do a terrible thing in the next 2 slides, which is really unforgivable in a general audience. I'm going to not only show you the equation for Bayes' rule, but I'm going to derive the equation. Now, if you hate maths and you can feel miserable now, it's only 2 slides. If you don't follow these 2 slides, it will make no difference to your enjoyment of the lecture, which you won't enjoy anyway. No, it will make no difference to your enjoyment. So just have a rest. But the formula is so beautiful and simple and has such profound implications, I thought you might want to see how you derive it. So the idea of Bayes' rule is you're going to generate beliefs about the world. And what are beliefs? Well, beliefs are things like, are my arms in this position or this position? Am I looking at a polar bear or a cat? What time do I think this lecture will end? These sorts of questions you might want to generate beliefs about. And Bayes' rule says there are 2 sources of information. There's data, and the data comes in the form of sensory input. Okay, that's all the data you can ever get from the world, sensory input, things from your eyes, your ears, your mouth. But there's also another source of information, and that's prior knowledge. You can have memories, or you can genetically encode information. And the key idea of the Bayesian formulation is that you're going to represent your beliefs about the world in terms of probabilities. So a belief will be represented by a probability with a strength between 0 and 1. 0 means I completely don't believe it. 1 means I'm totally sure it's true. And numbers in between give you the levels of grayscale between certainty. So if I said to you, for example, I throw a fair dice, what's your belief? It'll come down as a 6. Well, we can write the probability or the belief the dice shows a 6 should be 1 in 6. That's straightforward. But I could also say, what's your belief that all ravens are black? Now, you may not know, we don't even know whether all ravens are black. We've never seen all the ravens in the world. So you might say, my belief is 0.95. I'm pretty sure. And in the Bayesian world, we're even willing to consider beliefs about something we can never know the answer to. So, what's your belief that Fermat would have understood the proof of Fermat's last theorem? So we're happy with those sorts of beliefs, and that's what we want to represent about the world. We need one more element before we get to Bayes' rule, and that's the idea of a conditional belief. It's the belief in one statement, given you're told another statement is true. So this little vertical line is just mathematical words for the word given. So what's your belief that a dice would show a 6, given that it's come down as an even number? Well, there are 3 even numbers. One of them is a 6, so it's 1/3. Okay, we have all we need now to derive Bayes' rule. And I'm going to derive it by an example. If you look at this room here, there are people in this room, and some of you may have a disease or not, and some of you may have some positive diagnostic test or not. And let's just think of a room of 10 people here. The ones in white have neither disease nor the positive blood test. The ones in blue have the disease, the ones in red have the positive blood test, and the ones with red and blue have both. So we could simply ask, choose someone at random from this room, what's the probability they have both events true about themselves? So the probability they've got the disease and the positive blood test, well, that's very simple. It's these 3 people here have got both. Out of the total number of 10, it's 3/10. Okay, that's the probability of choosing someone with both disease and blood test. But we can write that mathematically a different way. We can write it as the probability of one of the events being true, multiplied by the probability the second event is true, given we now know that this event was true. So let's just convince ourselves we get the same answer. What's the probability of a positive blood test if we choose someone randomly? Well, the red ones are the positive blood test, so that's 5 people out of 10. And what's the probability of having the disease if you've got a positive blood test? So we're looking at these people. Well, it's 3 people out of the total 5. And luckily, 3 times out of 5 times 5 out of 10 gives us our 3 out of 10. Or we can write it the other way around. We can start with the disease, which is now 4 people out of 10 who are blue, and multiplied by the probability of having the positive blood test. That's 3 out of 4, and we get the same answer. So this is just mathematically a consistency relationship among probabilities. But now if you've got an equality like this, in equations, we can divide both sides by the same thing, and it'll still be true. So let's divide both sides by the probability of B, and that's Bayes' rule. There's nothing mystical about Bayes' rule. It's just a consistency relationship among probabilities, but it's incredibly useful. Imagine you're a doctor, and someone comes in with a positive blood test. It would be very nice to know the probability of having a disease given you've got a positive blood test. That's diagnosis. And it turns out, using this equation here, you can work out the elements you need to compute to do that. Now, I'm not really interested in statistics. I'm interested in the brain. So what's all this Bayesian got to do with the brain? Well, let's relabel A and B as things the brain cares about. A is something we want to estimate about the world, some state of the world. And B is the sensory input we get. I get sense of the world, and I want to estimate things about it. It would be lovely to know the probability of different states of the world given my sensory input. So I get some input, and I want to estimate what state I'm in of the world. Well, it's hard to do in one go, but by plugging A's and B's into Bayesian, we get things which have intuitive appeal. So over here, we have the probability of different states of the world independent of sensory feedback. So that would be things like, how probable is it I'll see a cat today versus a polar bear? How probable is it my arms will be in this configuration compared to this configuration? So these are things I can learn throughout my life, learn the statistics of how the world operates. And that gives me my prior belief. Now, if I just use my priors, it would be like hallucinating. Just the most probable thing's always going to happen. So I have to ground it in reality. And the way I do that is by using this term here. They've got horrible old names like likelihood, doesn't really matter. This says, given a possible state of the world, how probable is my current sensory input? So if I believe it's a cat I'm looking at, how probable is my information on my retina compared to if I believe it's a dog I'm looking at? And what Bayesian says is I should multiply these numbers together, and what I get is my belief in states after sensory input, which is called a posterior. So it's a way of combining prior knowledge and combining sensory evidence in an optimal way to generate beliefs about the world. It's the best you can do if you can represent these things. Okay, enough equations. Let me give you a real-world example where Bayesian would operate. Imagine you're playing tennis, and you want to decide where the ball is going to bounce to return it. Bayesian says there are two sources of information. There's sensory evidence available on the current shot. So you can get that from vision, from audition if you want. And so you might say it's most likely to bounce at the spot here. But you should know that your senses are not perfect. Therefore, there's uncertainty. And you should know about how variable your vision is. So although that's the most probable location, this red area shows you the probability over the entire court. It's most likely here, less likely here, almost impossible there. And that spread of probabilities comes from the fact that you know something about noise in your system. However, there's a second source of information, and that's that the ball a priori does not bounce with equal probability over the court. If you're playing against a very good opponent, maybe they distribute the ball in this green area here. And so Bayesian says the right thing to do is to multiply the numbers in the green by the numbers in the red at each point to get your belief shown here, which is a different location. And 10 years ago or so, we showed in a number of experiments this is exactly how people behave. We are statistical learning machines. We go around the world learning statistics, and we also know about how noisy our own senses are, so we can integrate those two sources in a Bayesian way. Now, I would love to spend some time giving you motor control examples, but they're quite hard to demonstrate. So I'm going to give you a few examples of how we can use Bayesian to explain visual phenomena. So I showed you this example earlier, where it looks like the square is going left and right, when in reality it's going round in a circle. Why do you see it going left and right when it's really going round in a circle? Well, the sensory evidence you get is consistent with it going round in a circle or going left and right. They're equally valid sensory feedback for those two situations. But if I sent you out into the world and said, I want you to measure the speed of every object you can find, it's a lifelong project, but you're going to measure the speed of everything in the world, and I want you to come back and tell me the probability of different speeds. Here are speeds of 0, here's 10 meters per second, here's the probabilities. The most probable speed you're going to see is 0. Most things do not move. Okay? What about 5 meters per second? Well, there are going to be fewer of those things, and 10 even fewer. So in general, you have a prior belief that things move slowly. And when people have measured these sorts of things, it sort of falls off like this. So if you have a prior that things move slowly, the interpretation you're going to choose for this image here is the one consistent with the slowest speed Bayes tells you. And in fact, if the objects go left and right, it can move slower than one going round in a circle for the same image. In fact, this explanation is why when you drive on a foggy or misty day, you tend to think you're driving much slower than you are. As you remove good visual information, your prior belief that things are slow makes you speed. Oh. Okay. We talked about this example. Here's a nice image. You'll all see that as a cube, I hope. It's not a cube, it's just a bunch of lines on the screen. So why do you see this as a cube? Well, we can use Bayes' rule. The probability of getting this sensory input given these different states is equal. Each of these three-dimensional objects will give you the same image on the back of the eye. So they're all equally probable based on the sensory evidence. But what about the probability of different states? Well, the prior belief of these objects is not the same. You rarely see objects like this. You very often see cubes. So you choose the interpretation which is most probable given your memory and your sensory evidence, and that's why you see a cube. This is another nice example. If you look at this object, I think you'll see that on the diagonals these little bumps coming out, and over here little dips going in. I'm just going to take this object and rotate it upside down. That's all I'm going to do to it. I'd like you to focus on the diagonals, which are all coming out, and see whether in any way you change your view of those when I rotate it upside down. So hopefully, it should all have reversed now. You should now see this diagonals as going in. Why is that? Is that a faulty processing in your brain? No, it's the optimal processing. And the reason is, this is just a two-dimensional flat surface, this screen. All we have is little circles, which are either light on the top and dark underneath, or dark on top or light underneath. The only way you can work out whether they're coming out or going in is if you know where the light is shining from. Now, we live in a world where the sun and moon are above us, and the room lights tend to be above us, and so we assume the light is up here. And if the light is up here and things are light above and dark underneath, they're coming out. And if they're dark above and light underneath, they're going in. When I turn the object upside down, everything flips around. If you put people in a room with objects like this and make them feel the objects with light shining from underneath, over the course of hours, they could begin to change their prior belief to reinterpret visual scenes. This is a hard problem, vision. Without priors, it's quite hard to interpret objects. And just as a nice, difficult example, I just want hands up. Who can see the animal in this picture? Don't tell people. Just keep your hands up if you can see it. Okay, great. I'm going to tell you something about what's in this picture. Keep your hands up. It's a dog. Who can see it now? Put your hand up if you can see it and keep your hand up. Dog. Okay, it's a Dalmatian. So I'm giving you more and more prior information. Dalmatian. And its face is in the middle of the scene, right in the middle of its face. A few more people, it's a hard one. If I show you where the dog is, okay, and now I remove it, you're never going to forget that dog. You've now got strong prior information to interpret that scene. Now, this scene looks really noisy, but actually, when you get computers to look at visual scenes, they are really noisy and hard to interpret. Here's a nice example. I'm going to get this man to speak in a moment. And I want you to tell me whether he's saying da da or ba ba. And I want you to watch him while he does it.
Ba 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 ba.
Okay, can I hands up? Who thinks he's saying ba ba with a B? Who thinks he's saying da da? Okay, so you're all convinced he's saying da da. I want you to watch him again, and whenever you feel like it, not when I tell you, close your eyes. Okay, watch him.
Ba 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 ba.
And you can open your eyes again when you want and see whether it changes.
Ba 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 ba.
So with your eyes open, you're going to hear da da. With your eyes closed, you're going to hear ba ba.
Ba ba.
What is going on? Is this some terrible faulty processing on your brains? No, this is optimal processing. Hearing sound is not an easy thing for us. We use all the cues we can to interpret the world. And vision is a very powerful cue. Those who can lip read will know that. So in general, you get information from multiple sources. You get it from hearing, touch, sound, taste. And they're often about the same information. So in this case, the way this video is constructed is the sound was playing ba, 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 but the video came from a man saying ga, ga, ga. And because you've got noise in your brain, there's noise in the outside world, Bayes' rule comes into effect to say, how can I best come up with a percept which is the best possible given these conflicting sources. And it turns out, in that case, you get da-da out of it. Okay? Now, if you want to go on the web, this is called the McGurk effect, and you can find lots of beautiful examples of the McGurk effect and other illusions such as these, but it shows what a brilliant thing our brain is doing without us even knowing it. Okay, so I've talked that Bayes' which is the most beautiful formula, is really important, but there's a key element to Bayes' the calculation of this, which is non-trivial. I've got to say, what's the probability of getting the particular sensory input given a particular state? And that requires a prediction. I have to be able to say, what sensory input do I think I would get under this situation? So I want to talk a bit about how the brain does prediction. And the idea is as follows. You send a movement command down, it causes the body to change shape or cell state, and you get sensations from vision, from the skin and muscles. And the transformation from the commands out to the sensations you get back are governed by the physics of our body and our sensory apparatus. But we can think what's happening inside the brain. Here's my drawing of the brain. You can imagine that the brain may have a predictor inside it. So here's a little neural predictor sitting inside the brain. And what it would do, it would take a copy of that movement command and predict the sensations I think I'm going to get. So here are the sensations I really get. I'm shaking a ketchup bottle. I get the sensations as a function of time. Here's my prediction. And you can see how you would learn this prediction. You compare this prediction to what I actually get and sort of train the predictor to be better and better. So the idea is, as I go around the world, I'm predicting what sensations I think I should get. Why would I bother doing that? Because I'm going to get the sensations anyway. Well, there's a bunch of good reasons. I'll just give you one today. And that is that not all events are generated by my own movements. They're also external events. And in general, I want to be much more aware of external things than feeling everything happening inside my body due to my own movements. So one way to deal with that is if someone comes here and very gently, kindly taps on the ketchup bottle for me, I get another sensory input due to you. So this is you, this is me, but they're combined together into one sensory input based on what my receptors report. So how can I recover what you did? Well, the easy way to do that is to predict what I would get just based on me, subtract it off from what I'd get, and anything left over is you. So it's a way of going around the world predicting everything I do and everything left over is external. Okay? It's much cleverer than those noise-cancelling headphones because it has to make a prediction rather than just invert a signal. So, what evidence is there the brain does this? Well, again, about 10 years ago, we thought, what's the most obvious example of when you do something to yourself, it feels very different than when someone else is doing it? And the obvious thing to us was tickling. We know it's hard to tickle yourself, and people have studied this for many years. Why is it? People have hypothesized that just the mechanism I described could explain it. But they weren't able to convincingly prove it because they didn't have the technology needed. So we can bring those experiments to the 21st century by applying robotic technology. So the idea is we have a stick in one hand attached to a robot, and the subject can move that back and forward. And we can track that with a computer and control another robot which holds a small stick which is going to tickle the subject's palm. And then we're going to ask them to rate various things, including ticklishness. And the first thing we do is replicate old studies with our apparatus. I'm not showing you the robots, but they move back and forward here, and we replay it as accurately as we can to the other hand, as though it's a single stick. So if we get the simulation right, it's like doing this, even though the sticks are separate. And then in the same subjects, this hand is now still, and we replay the tickle that they get in this condition. So the left hand gets the same input. In this you cause it, and this you don't. And no surprises, this one is significantly less ticklish than this one. So it works. But there are many explanations for this. One possibility is when I do something to myself, just turn the volume down non-specifically. And what we really want to know is, are they making a precise prediction? And to answer that, we can put some perturbations in. We can have people move back and forward with this hand and now replay it to the other hand with a time delay. Either 0.1, 0.2, or 0.3 second delays, very short delays. So the important point here, this hand does the same movement, just goes back and forward. This hand gets the same input. All we're playing with here is the temporal causality. And as we go from 0 to 1.1 second, it becomes more ticklish. Up to 0.2, it's more ticklish again. And by 2, it's equivalent to just the robot tickling you. So you're very attuned to variations in temporal causality. Rather than put a time delay in, we can put a rotation in. So now the hand goes in one direction, and the tickle stick goes at 30, 60, or 90 degrees. And again, as the discrepancy increases to 30, it becomes more ticklish to 90, and by 90, it's equivalent to external tickle. So it says to us that what's responsible for cancelling the sensation is very tightly coupled to spatial and temporal causality, and the only thing which makes sense is that the brain is making precise predictions. Now, these experiments were very messy experiments. The hand is not very ticklish. We need large numbers of subjects for this. So in the intervening years, I was looking for an experiment I could do on individuals for various patient-related reasons. And I had 2 children those years. These are not my children. I have 2 girls. But what you'll know on the back seats of cars on long journeys, if you have 2 children, is they get into fights. And the fights always go the same way. One child does something to the other retaliates, the other one retaliates more, and it just quickly builds up to escalate. Now, my children would do this, and when I would scream at them to stop, occasionally they would both claim the other person hit them harder. Now, I know my children never lie, and so I thought as a neuroscientist, I had to explain how they could be telling inconsistent truths. And so we hypothesized when one child hits another, they generate the command to make that movement. So they predict the consequences on the hand, subtract it off, like in tickling. But the child who's hit is passive, feels the full blow, and if they retaliate with the same force, the first one will think it's been exacerbated. And so we hypothesized in these tit-for-tat games, maybe it's this predictive thing which is making things escalate. So we decided to test this in the lab. Now, we don't work with children with hitting, but the concept is very simple. We bring in 2 players, and each one puts a finger under a little force transducer so we can measure the force attached to a lever of a motor. And the game starts with this motor generating a very small force on the subject's finger. Player 1's been told, remember that force, and use your other hand to apply the same force down onto the other subject. So they apply the same force, and then they stop. And player 2's been told, remember that force, apply it down to the other subject to close the loop. And they do that. Importantly, the 2 players are given the rules of the game in separate rooms, so they don't know the rules the other is playing by. And so we carry on this game for 5 or 6 turns, and we measure the force on each go. So here is the number of turns, here's the force we measured in newtons, and here is perfect performance. This is the force the robot started off with. And what we see in all pairs of subjects is this: a rapid escalation in the force up to the point where it's painful on the finger. And if you ask the subjects, what rule do you think the other person was playing by, they say things like, well, they were clearly doubling it each time. So there's a huge amount of attenuation of the consequence of our own action on others and on ourselves. And what we've shown in a series of studies, this is a predictive phenomenon. Okay. It's also true of other things we do, so sound as well. When I speak, and you're supposed to judge sound levels, I will think I'm speaking much quieter than I really am because I attenuate the sound that I speak. So I want to convince you with an experiment you can do on yourselves, the brain does make predictions, because it's hard to do some of these robotic type ones, but here's one you can do. And I'm going to ask you, first of all, before we get to the experiment, to consider the following. I'd like you to focus on this dot here, and as the bird flies by, you'll get a very strong impression the bird flew past. What's happening? Here's a cross-section of your eye. The bird is on the back of the retina. As the bird flies by, the bird goes along your retina in the opposite direction due to the lens. Now I want you to instead follow this dot across the screen. So if you follow the dot, your impression will be the bird did not move. And what happens at the back of the retina as you moved your eye? Well, the bird again moved along the retina. So in both situations, from the retina's point of view, the back of your eye, you can't distinguish the 2. The bird just went across the retina, even though in one you felt the bird moved, and the other you felt that you moved. So there must be something telling you where your eye is pointing. Because if you know where your eye is pointing and where the bird is on your retina, you can know where the bird is in space. So how do we know which way our eye is pointing in our head? Well, about 100 years ago, a man called Helmholtz thought of 2 ways in which you could tell. One possibility is you could have sensors in the orbit or in the eye muscle. Somewhere inside near the eye, you sense which way your eyes are pointing. That's a very sensible thing to think about. But there's another possibility. You could do it based on prediction. You send the commands down to your eye muscles to move your eyes. A predictor could predict where your eye has gone. Okay? Seems bizarre, doesn't it? Okay? So how can we test between the idea you're going to predict where the eye goes or you're going to sense where the eye has gone? Well, imagine you move your eye in an unusual way. Imagine you use your finger to rotate your eye. Okay? What are the predictions of these two hypotheses? Well, the top hypothesis will say you've got sensors. You'll know that your eye has moved. So even though the bird has moved on your retina due to rotation by the finger, you'll know that your eye has moved, so the whole world will be stable. But on the other hand, if you need this predictive mechanism to know that your eye has moved, then you'll think your eye is in the same position, and the bird's moved, therefore the whole world must have moved. So now this is an experiment we can do. Now, I don't want to be sued by 280 people, so before you do it, let me tell you what you have to do. You cover one eye with one hand, and you can push quite hard through your upper eyelid, not directly on the white, through your upper eyelid towards your nose, and see whether the world stays stable or the world moves. Okay? So just push gently towards your nose with one eye closed. Does the world stay stable or move? It moves. And that's the first evidence that the way you know where you're pointing your eye is through prediction. Okay? The even more amazing experiment, which was done many, many years later, is you can use curare to block the eye muscles. Okay? So you inject curare into a human's eye muscles, so it's frozen, they can't move the eye. You then ask them to move the eye, and they send the command down, the eye doesn't move, but they predict the eye has moved, even though the image doesn't change because the eye hasn't moved, and they see the whole world move. So the reason you can do this for the eye is the eye is a very predictable part of the body. Nothing really perturbs the eye. Whereas for the arms and hands, the way you know where they are is a mixture of prediction and sensory feedback. Okay, in the last few minutes, we've done all our inference about the world using beautiful Bayesian statistics, but there's no point generating beliefs if they don't lead to actions. So we need to think about how we generate the actions in an optimal way. And the problem we have is any task, however simple or difficult, I want to dance, pick something up, there are infinitely many different ways you could do it. Okay? So take a simple task, reaching from this point in space to this. I could move along this path, it's a bit jittery, sorry, or this path, or infinitely many other paths. There's so many paths you could choose. If I choose a particular path, I can hold my arm on that path with infinitely many different joint configurations. And if I choose a particular configuration, I can hold my arm there really stiff with my muscles contracted or really relaxed. Huge amount of choice. So when we move, do we all just choose our own way of moving, or are there some principles governing our movement? Well, there have been thousands of really tedious studies showing we all move in a very similar way. And we move in such a similar way, the brain has dedicated circuitry to extract information from the biological motion, the way we move. So if I take these dots here and set them in motion, even though it's a very poor representation, because it's biological, you'll instantly know what's happening. You'll know if this person's happy or sad, old, young, male or female. Okay? So we have amazing circuitry to extract biological motion and make it meaningful. If these dots were cars going around a racing track, you'd have absolutely no idea. If I set this one in motion within a few hundred milliseconds, you'll know exactly what's going on, even though it's a bunch of dots just moving randomly on the screen to some extent. And although we all move the same way, people can make their early careers by violating biological motion. So this is John Cleese on his way to the Ministry of Silly Walks from Monty Python. And that somehow is funny when people violate biological motion. So why do we move the particular way we move? And we come back to sort of evolutionary arguments. Maybe we don't all move the same way. Maybe some of us move in a better way than others. And those who move better have got more chance of getting their children into the next generation. So movements improve over generations. And maybe within our lives, our movements improve through learning to be as good as they can be. And the question is, how do you measure the goodness of a movement? What limits how good our movements can be? And we come back to the idea of variability or noise. It turns out it's hard for us to make precise movements. When we play darts, we scatter those darts all over the place. And if you measure the variability, this is the force measure. If you just ask people to generate forces against a force transducer of 1, 2, 3, and so newtons, although on average they can match the desired force, you see variability around that force. And what's very characteristic of our movement system is the bigger the force, the more the variability. And that's why when you try to move fast, you're not very accurate. You've got to move slow to be accurate, keep the noise low. Why does this sort of noise help us solve the problem? Well, it does. Because we have many ways to move, we can consider the consequences of that noise on the movement. Imagine I want to catch this ball. I could choose to catch it here or the same point here. And here are two possible paths I could choose out of the infinite number of paths. If we consider this path here, that specifies the forces in, let's say, one muscle as a function of time to achieve that path. But that's what I want to do. What I actually get is a noisy version, with more noise for big commands, less noise for small commands. Which means if I was to replay the movement many times at the same point with the same desired commands, because the noise is different every time, I'll get variability due to the movement. And I might, for example, in this case, have variability that looks like this. If I, for example, start here and generate a different movement, I'll have a different command, different noise, playing through a complex system. All bets are off. The only thing I can be 100% sure about is the variability will be different. And in this case, maybe my variability over repeated movements would look like this ellipse here. So if I say to you, which way would you rather move, hopefully you'd all choose this way because the variability is smaller. And in general, you could ask, what's the way I should move to be the best variability or the least variable I can be? And that's the theory which we've developed. The idea is you've got this noise, and by choosing different ways to move, you can effectively control your variability. And depending on the task you want to do, you want to move in such a way that the bad consequences of noise don't play through. Now that's true for sort of movements of the arms and hands and eyes. But when it comes to pedaling your bicycle or running, energy is much more important. So when you model walking, we think of starting in one pose, ending in the same pose, and minimizing energy. Now, I could choose to be really accurate and never, ever trip, but I'll use up a lot of energy. So when I'm walking, I'm willing to occasionally trip to save energy. When I'm using a knife and fork to feed myself, we think energy is much less important. It's much more important to get the food into your mouth than the fork into your face, than save a bit of energy. So in general, we think of movements now as a trade-off between energy and accuracy, and you can put more energy in if you want and to get more accuracy, and vice versa. So I studied the control of movement because I think it's fundamental to understanding the brain, but it also has some implications in the real world. There are many diseases which affect movement, from stroke, multiple sclerosis, motor neuron disease, and so understanding the basics of control of movement can begin to inform us about some features of those. It's also useful rehabilitation for diseases. If we understand normal control of movement and learning, we can harness that to help in patient care. And clearly, if we understand the control of movement in humans, we could apply some of that technology to robotics to improve robotics, which has solved the task in very different ways. So I want to remind you finally, when you see creatures doing very simple movement tasks, don't forget the complexity of what's going on inside their brain. Thank you very much. Thank you so much.